Elizabeth is going to go first, and then Aaron. But we can adjust to that also. Okay? So, Elizabeth.
Okay, thank you very much for inviting me here to speak today. I'm going to be talking about a theoretical analysis that we did for a particular class of problem instances that allows us to obtain rigorous results on the asymptotic performance of simulated quantum annealing, and also compare that with rigorous results for quantum annealing and classical simulated annealing. So the first version of this work we put on the archive in January, but I just put an updated second version on the archive last week that made some corrections and also expanded the scope of the results by a bit. And just recently this work was also accepted to Fox 2016, which is a computer science conference that'll be held this November. So I'm going to be taking the approach of comparing quantum annealing to other meta-heuristic optimization methods. And in the language we heard earlier this morning, these are non-tailored sequential algorithms. That is the big three: quantum annealing, simulated annealing, and simulated quantum annealing. Now, how are we going to answer the big question of how useful is quantum annealing? Well, we've heard some about empirical tests. So far at the conference, you can build or numerically simulate quantum hardware and benchmark it on random instances. But another kind of approach, the approach I'll be taking, are theoretical tests. So here, you may have things like analytically bounding the spectral gap of a quantum annealing system in the regime where the noise is low enough for the adiabatic theorem to apply. Or you could do some work to theoretically bound the efficiency of classical simulations of quantum annealing. And in particular, I'm going to be focusing on simulated quantum annealing, which is a classical algorithm for sampling the output of some quantum annealing systems, including the transverse field that we care about. But in general, the performance of simulated quantum annealing is still very much an open question, at least theoretically. We're starting to get a pretty clear picture empirically. So let's go over the special properties that make simulated quantum annealing possible. Well, we know it's possible when the Hamiltonian has no sign problem. Or put another way, the quantum annealing Hamiltonian has non-positive off-diagonal matrix elements in the computational basis. This immediately implies that the thermal density matrix is a non-negative matrix. It has non-negative entries everywhere. And you can see this just by expanding that exponential as a Taylor series and noting that each of the terms in the sum is non-negative. Okay, but if we take the limit as the temperature goes to 0, then the thermal density matrix becomes the ground state. So this is also an argument that says that the ground state of a Hamiltonian without the sign problem has non-negative amplitudes everywhere. And this property of the Hamiltonian is called being stochastic, which is a combination of the terms quantum with the term stochastic from the field of stochastic matrices. So let's talk a little more about the specific kind of simulated quantum annealing that I'll be analyzing. So this is based on the path integral quantum Monte Carlo method. One way to quickly explain how this works is that you want to express the partition function as a discrete path integral. So you see, in the first step, I've just expanded the definition of the trace, and I can do this trivially because the Hamiltonian commutes with itself. And then here, I've just inserted several copies of the identity. L is some integer parameter that sort of controls the discretization that we've done for the path integral. And so the property we talked about on the previous slide, that the off-diagonal matrix elements are non-positive, that implies that these weights are all positive. The terms of this sum are all positive because they're e to minus some positive real value. So this creates a probability distribution on the space of paths. Okay, I'm not going to have to get into the Trotter-Suzuki formula or anything, because this kind of illustrates the fundamental difference between more general kinds of quantum systems and this restricted class of stochastic Hamiltonians. Because, so Feynman told us that when you have a genuinely quantum process, you have all paths contributing with some phase. And all those phases, of course, have the same magnitude. But for a stochastic system, some paths are more important than others. Okay, so it's somewhere in between the classical regime, where you have one path that minimizes the action, and the quantum regime, where you really need to count all of the paths. So when you have a distribution that places more importance on some paths than others, you can start to think of exploiting a general randomized algorithm called Markov Chain Monte Carlo. So I'm going to break down these terms because we often just say them together, and I want to break down what they mean separately. So Monte Carlo means that you're estimating expectation values for a distribution by only sampling a small number of points instead of summing over the whole domain. Now, but this leaves the question, how do you sample these values from some complicated distribution pi? And that's where you use a Markov chain. So a Markov chain is a random walk that takes place on the domain of your probability distribution. And the way you construct this random walk, or a sufficient way to construct this random walk, is by designing it to have transition probabilities that satisfy this detailed balance property. And so I think in the physics community, we usually characterize the performance of a randomized Monte Carlo Markov chain algorithm by something is called autocorrelation time. I'm going to use a slightly different concept, which comes from computer science, called the mixing time. So this is the number of steps of the random walk that need to be executed to be close in trace distance to the intended distribution. And as we know very well in quantum information, once you're close in trace distance, this preserves all of your expectation values. Okay, so that's the formula for the mixing time, but if you haven't seen that before, just keep in mind that the mixing time controls your convergence to the intended distribution you wish to sample. Okay, so now I'll get to the particular class of instances that I'll be analyzing, and of course, they're bit-symmetric cost functions with a tall, thin spike. In fact, so their energy plot will look like this, or this is maybe the first example. We'll actually generalize this a bit on the next slide. But what you see here is on the horizontal axis, you have this, your domain, it's controlled by Hamming weight. So it's important to keep in mind that this is really a spin system, but we're viewing it as one-dimensional because the cost function only depends on the Hamming weight. Okay, and so the way the cost function works is it's entirely, it just scales up with the Hamming weight, except for this one special point where you introduce a tall, thin spike in order to create a false local minimum here. And this false local minimum, it was shown in 2002, makes the problem take exponential time to solve with classical simulated annealing, simply because it takes exponential time to even propose or to accept a proposal to step onto that spike. But it was also shown in this work that this problem can be solved in polynomial time using a quantum annealer. And so this was kind of the origin of all these tall, thin spike problems that we've been talking about. Now, let's look at a small generalization of this, where we now, so you might say, when you look at this, you might say that, well, what if I allow my simulated annealing algorithm to take steps of size 2 instead of size 1? Then it'll still solve this in polynomial time. So to defeat that, we're going to scale the width of the barrier polynomially. Okay, so the height of the barrier is n to the a, and the width of the barrier will be n to the b. And so now I'm going to go through an argument that was given in 2004, which explains why the quantum annealing gap of this system is constant when a plus b is less than a half. It's a nice argument, and it'll also create a nice parallel with what we do in the proof about simulated quantum annealing convergence. So the spikeless Hamiltonian, H tilde, has an order 1 gap. And we know this because the spikeless Hamiltonian means that, that this spike term is not here, and so the cost function simply depends on the Hamming weight, And so it is a collection of non-interacting qubits where each qubit prefers to be, a 0 in the sigma z basis. So it's an exactly solvable system when the spike term is not there. And it has a constant gap, and you can also see that the ground state probability distribution, viewed as a function on this Hamming weight basis, is a binomial distribution. And so the amount of probability that it can put in any one location has to be less than 1 over square root n. So now the next fact we want to point out is that adding this spike term, because it's a positive semi-definite operator, does not decrease the energy eigenvalues. They all go up, right? So these E tilde sub I is less than E sub I for all I. Now, putting this together, the argument that Reichardt gave in 2004 is that we can use the ground state of the spikeless distribution as a variational ansatz. We can use the variational method of quantum mechanics to upper bound the ground state energy. And so when you form that inner product, that expectation of the energy, you get that you have the ground state energy of the spikeless system plus some term that asymptotically goes to 0 when A plus B is less than a half. So because the first excited state energy does not go down, this implies that the gap of the spike system is constant when A plus B is less than a half. And the intuition is that quantum annealing does not even feel a modest size spike in this problem. In other words, the wave function really doesn't need to change all that much in order to minimize the energy. Okay, so now we'll get to the new results, which is simulated quantum annealing for the spike. So we show that simulated quantum annealing equilibrates in polynomial time and finds the minimum of the spike cost function whenever A plus B is less than a half. And in terms of explicit bounds, we find that it takes order n to the 17th time with single site metropolis updates, or order n to the 7th time with worldline heat bath updates. Now these O tildes simply mean that we're ignoring logarithmic factors. So here are some of the key ingredients for the proof. Okay, so just to say what this means is that simulated quantum annealing works in polynomial time. So does quantum annealing, but simulated quantum annealing takes exponential time. So from these results, you can conclude that simulated quantum annealing can be exponentially faster than classical simulated annealing. Now, the proof idea is that we're going to compare the simulated quantum annealing Markov chain with and without the spike term. We're also going to relate the typical proper time so here proper time means time along these world lines, these quantum Monte Carlo configurations. We're going to relate this typical proper time to the expectation values of the quantum system. And you might say, wait, we already know that because that's the whole reason we use quantum Monte Carlo is that it relates to the expectations in the quantum system. But we don't just want the mean values to agree. We want the distributions to closely agree. We want a concentration of measure within this measure that we put on the space of paths. We want to say that the proportion of the world lines that they spend sitting in the region of the spike is never that different than what the quantum system itself does. And then finally, on a more technical note, what we really prove is quasi-equilibration of simulated quantum annealing within a subset of the quantum Monte Carlo state space. And we use the adiabatic path to guarantee warm starts in this subset. So, of course, a key feature of Markov chains is that they, after you run them for a long time, forget where they came from. And in fact, that's what the mixing time notion also says. But what we're going to do is we're only going to let our algorithm live in this physically important region of the state space and show that it quasi-equilibrates there and that we can keep ourselves in this region with high probability using warm starts from the adiabatic path. Warm starts means, if you don't know that term, it means that you're in a distribution that is close to the intended one already as soon as you start running the Markov chain Monte Carlo. Okay, so now a little bit more background on Markov chains and mixing times because, I want to say this is meant to be this is meant to complement the methods that we saw earlier this morning. We heard about escape rates and instantons and all this beautiful physics, and I'm a physicist, so I like that stuff too. But we're going to use completely different proof techniques that come from the theory of Markov chains. So Markov chains, essentially you can think of a discrete time Markov chain as corresponding to its transition matrix. This is a stochastic matrix because, well, what that means is that the rows sum to 1, and so if you apply this matrix to a vector that represents a probability distribution, then you get another vector that represents a probability distribution. A stochastic matrix conserves probability. Okay? And in terms of the random walk, this means if you start at the point x, you always have a probability of going somewhere. Now, with this definition, the stationary distribution will be the eigenvector with the largest eigenvalue. And it has eigenvalue 1. Okay, and you can actually control the mixing time. That's what this tau epsilon is. The time it takes to be within trace distance epsilon of your target distribution. You can control it with the spectral gap of this Markov chain transition matrix. Okay, so it scales essentially inversely with the spectral gap. And then there's this factor of 1 over pi min, but it has a log that makes it typically not as important. But this 1 over pi min really characterizes that your random walk, we're considering the worst possible starting point for that random walk. Okay, so let's talk a bit about how, so, you know, we know as quantum annealing aficionados that analytically determining spectral gaps is very hard. And so we need additional tools that also characterize the mixing times of these Markov chains. And one of the most beautiful tools is this idea of conductance and bottlenecks. So we're going to visualize our Markov chain, pi p omega, as a weighted graph. The vertices are the states x of our domain. And 2 vertices are connected with an edge if there's a non-zero transition probability between them. So with this picture in mind of this weighted graph where the vertices have weights and the edges have weights, then the conductance of a set is the probability of leaving some subset of the graph over the probability of being in it in the first place. Okay, so this phi of s quantity, here we have in the numerator, we have this sum over all the states that are on the boundary of S that also have an edge leading outside of S, right? So let's think about this conductance. If it's large, then you have a high probability of leaving the set S compared to staying in it. But if this quantity is very, very small, then that means that you have a large denominator, you have a high probability of being in S, but you have a small numerator, a low probability of ever leaving S, right? So you can already get the idea that this is going to imply slow mixing because you're trapped in the set S. And here, just a technical note that pi of S should be less than 1/2. It shouldn't be the full state space, because if you're going to talk about it getting trapped, well, you know, there have to be important regions outside of the set S as well. So anyway, if you take the minimum over all of these subsets that are less than 1/2 of the weighted state space, if you take this minimum, then Cheeger's inequality is a result that relates this to the spectral gap of the transition matrix and therefore to the mixing time of the Markov chain. Okay. So essentially what this says is that the Markov chain is rapidly mixing. The mixing time scales polynomially with the system size if the state space graph has none of these bottlenecks. Now, even the conductance turns out to be pretty hard to work with in practice. So we're going to go one more step removed and look at a technique called canonical paths. So what you do here is you design paths such that between any 2 vertices, they carry an amount of probability traffic, pi x, pi y, for those 2 vertices. And you design these paths in such a way that they don't overload any of the edge capacities, that is, the probability of being on that edge and actually taking that transition. So this leads us to a quantity called the congestion, which is the worst case ratio of the total traffic of paths passing through an edge to the capacity of that edge, right? So in the denominator we're taking a maximum over edges of this quantity that we think of as the capacity, and then we're summing over all the paths that pass through that edge of the traffic, and we also need to account for the length of the path. And when you define this quantity, it was shown maybe in the early 90s that this can be used to bound the mixing time of your Markov chain. So our proof is going to be very much based on these canonical paths. So here's the idea. The configurations, the quantum Monte Carlo configurations, which do not spend too much of the proportion of their world lines sitting on the region of the spike, will have a stationary weight in the spike distribution, the QMC for the spike system, that is very close to their stationary weight for the QMC for the spikeless distribution. So this leads to a picture of the state space where we have this large region, omega G, omega good, colored in yellow, of states where the weight of the configuration, because, okay, think about it. So if the spin configuration never touches the spike, then it's going to be identical in the spike QMC and the spikeless QMC. So most of the state space, actually, these distributions actually look quite similar. But there are also these holes. So omega B is really the union of all these holes. It's the bad region. It's the bad region where the QMC configurations spend a lot of time on the spike, and so their stationary weight looks very different than that of the spikeless case. So the new proof technique we used is that we showed that you can use most of the canonical paths from the spikeless distribution to construct a set of canonical paths for the spike distribution with congestion of the same order. Albeit it's inside of a subset. It's inside this subset omega G, which doesn't have measure 1, but measure 1 minus 1 over poly in n. So in other words, we're trying to cut off a small part of the state space that isn't going to mess up our expectation values, but does make it very hard to see that the simulated quantum annealing chain would mix in this region. In fact, maybe it doesn't mix in this region, right? At some point, we believe the adiabatic path should be a necessary inclusion to get simulated quantum annealing is QMC plus the adiabatic path, right? And we need the adiabatic path to stay inside the good subset omega G. Okay, so now I'm going to go through maybe some technical calculation stuff or just talk it through. So when we're talking about heat bath world line updates, so here x1 bar through xn bar, yeah, think of these as the world lines of the n qubits, right? So of course the quantum Monte Carlo configurations are these length L sequences of n-bit strings, but here x1 bar is just a length L sequence of bits, the world line of that qubit x sub I. Okay, so how does a heat bath world line update work? I know a lot of you know this, because you've implemented. So you're going to select one of the world lines uniformly at random. You're going to leave all of the other world lines untouched. And then you're going to resample the world line you selected. You're going to delete it and resample it from the conditional distribution that is conditioned on all the other spin values. It's completely standard. Now, the congestion for this Markov chain for the spikeless distribution, all my tilde quantities are the spikeless system. The congestion turns out to be order n squared. And it's essentially because the paths have n steps. And in this step, where you select a single I, that means you have a 1 over n probability of selecting any particular world line. So this bound, you can already see, is not tight. Because this is a non-interacting spikeless system, we know that the heat bath world line update should mix in time n. Right? As soon as you the world lines don't interact. So as soon as you touch a world line, you never have to come back to it. You're sampling it straight from the stationary distribution. So this bound is not tight, but the reason we need to use it is because it's the tightest bound you can get with the canonical paths technique. And our comparison method doesn't port the mixing time. It doesn't say the mixing times are the same. It says if you have a set of paths for one of them, then you can construct a set of paths for the other. So that's why we lose a little bit of tightness on this bound. Now, I also want to discuss that if we're using if we're treating this as a non-tailored metaheuristic method, then these heat bath world line updates actually take some non-trivial time to implement. In other words, without using the symmetry of the problem. So the way this works, well, first let me say in words how we implement heat bath world line updates. Right? So you've now deleted this world line after selecting it. You now have to look at all the other transitions in the rest of the system and break your world line that you're updating into these time segments, right? And you also need to introduce So breaking it into all of these time segments, and then you compute the effective potential due to all the other spins. That's what the conditional distribution means. Now you also need to generate some new jumps in the world line that you're updating. So let's take what I said in words and count up the factors to get to this bound. So we know with high probability there will only be order beta log n jumps per any given world line. And this is essentially because it follows a binomial distribution with mean beta. I'm using so my adiabatic transverse field is just order 1, so that's why that doesn't appear. Otherwise it would be gamma times beta, where that's the transverse field. But you also have to account for these deviations away from the mean. So that's why this log n has to be there. If it weren't there, then we wouldn't get the right expectation values. Now, I said you count up all the other jumps in the rest of the system to create your effective potential. Well, there's going to be n beta log n segments there. And then finally, when as you're going through and flipping a weighted coin to decide what these new blocks are, you have to check all the spin values in all of the other world lines. So again, you might say, like, what is the point of doing things this way? Why don't you take advantage of some obvious speed ups you could get? But we're really trying to make a fair comparison. And if you do that, then the best you can get is order n squared beta squared. Okay, so now we're ready to kind of put everything together and sketch what the whole proof looks like. So the congestion of the spikeless chain is order n squared. And the congestion of the spike chain is of the same order in this set omega g. So this implies that the mixing time within the set omega g is order n squared log pi min. Now, pi min is just our worst case starting point at each step of the adiabatic path. In fact, here's how we can analyze pi min. So if you look, if you're familiar with QMC, you know that the thing you pay for most, the thing that most lowers your weight of your configuration are having lots of imaginary time jumps. But because there can only be order beta log n jumps in any particular world line, then this sort of pi min scales this way once you've taken the log. Okay? Now, the other thing we need is that it suffices to take essentially this linear schedule in order to fulfill the warm start condition. Let me just briefly say what that is, because so you're running the chain inside of omega g. And if you start very close to pi, then you only have to run the chain for a very short time inside of omega g. If you had to run the chain for too long, you would have too high of a chance of going into the bad subset. So that's why you have this sort of window, not too short, not too long, for which you can run the chain and still stay in the good subset omega b. And to do that, you need steps at least this small along your adiabatic path. And as we saw in the previous slide, one step of the world line update chain takes time order n squared beta squared. So finally, if you count all these factors together and use the fact that we actually have a beta that scales with n, and this was necessary in order to sort of defeat the density of states and be close enough to the ground state to make those properties I said about the distribution being very close hold. And so if you put all these things together, then you can get this upper bound of order n to the 7th runtime. And I think that's essentially the best you can do with a fair comparison that isn't, we haven't optimized the adiabatic path or anything like that. We're just trying to run it as a black box. And I think that's about as tight as it's going to get with this method of analysis. Okay, so we've shown that simulated quantum annealing can inherit some of the advantages of true quantum annealing, and this allows for a provably exponential speedup in the asymptotic performance provably exponential separation in the asymptotic performance of simulated annealing and simulated quantum annealing. Can we leverage the ideas in the proof to better understand the stationary distribution and convergence properties of SQA and more general systems? You notice a lot of the techniques that I sketched don't actually use the bit symmetry of the problem. Really, the best thing that gave us was that we were able to solve the spikeless case, and we knew so much about the wave functions. Lastly, the future is bright. There is a lot to do. Thank you.
Okay, we have time for questions. Okay, Daniel, I think I'll give you this.
So are you able to relate this speed up to tunneling or some other nice quantum feature?
Interestingly, we did not necessarily take that approach. So the previous talk did a very good job of showing us what the tunneling looked like in terms of the generation of this instanton. But here we had almost a completely different set of proof techniques. So admittedly, we don't actually see the tunneling necessarily, but we have used the fact, I mean, I think what generalizes about this is the fact that we had a case we could solve, the spikeless case. And we had a case where we introduced the spike and it didn't change the wave function too much. And so now that we've shown that the simulated quantum annealing distribution picks up not only its mean values, but its higher moments from the quantum wave function, that this situation, if you have rapid mixing in the, in the spikeless case, your base case, then in the case that's not too different, now you can have rapid mixing there as well. So tunneling is great, but that's not the proof technique we used.
Okay, go ahead. Go ahead, please.
Yes, so hello.
Hi.
I admire very much the ability to do analytic bounds like this.
Sure.
If I tried to do that, I would not be able to compete with you. The best I can do is numerically simulate things brute force, and I've done that for some of these problems that you discussed. And I find that when you include the interaction of the system with a bath,
Yes.
sometimes we can get things that are slower, sometimes faster than the adiabatic theorem would tell us.
Yes.
So in one of your last slides, you said that this is the tightest that this bound is going to get. And I wonder if you have also explored what these bounds start to look like when you simulate. I haven't seen analytic bounds when you have a system coupled to a bath.
Absolutely. That's a good question. Let me say a few things. So when I say this is the best I can do, please let me qualify that by saying I'm very much following this black box approach. You must run it adiabatically. You must converge to equilibrium. Once you start relaxing those conditions, you can solve these problems in constant time. You can just rush to the end in a fully diabatic way. Daniel's group has this paper where there's a diabatic cascade that allows you to solve these types of problems in constant time. So it's meant to be a toy problem. I mean, the value of the toy problem is to run our methods the same way that we run them on more complex problems as well. Now, as for finding a theoretical analysis of these diabatic transitions, essentially the specialness of stochastic Hamiltonians pertains to the ground state or the thermal state. And once you leave these states, well, you're running into sign problems all over the place, and we might have to download that open source package.
Okay. Would you like to ask a question? Here we go.
So, can you generalize your technique to treat other kind of word line moves, for example, worm-like moves where you open word lines, which typically are more efficient than closed worm?
Absolutely. So first of all, the proof as written. So when I started this work, I didn't know that you were going to discover how good open boundary condition quantum Monte Carlo are, or some people in this room have now found that. That's a relatively recent development, but the same proof applies. And I've also been looking at things like, you have worm algorithms, right? These are more for condensed matter systems. Yes, some of the same proof techniques do apply. I just want to say that when you have heat bath worldline updates, these didn't appear in the first version of the paper because these canonical paths, you think of them flipping one bit at a time. Once you have these hugely non-local updates, it does kind of make the analysis more difficult, but yeah, I have some projects in the works that are looking at things like the worm algorithm, yes.
We'll have just one more question.
I've got a mic, thanks. So I got sort of two questions. One is just clarification. So in your final algorithm, you have to run it, you want to quasi-equilibrate a little bit.
Yes.
Not fully. So that means you don't want to run it too long.
Yes.
So you've put a lot of effort into making sure that you're just treating this as a black box. But how do you know when to stop running it? Does that depend on the specific problem, specific Hamiltonian?
Okay, I mean, I think that's a fair question, and the most I can answer there is that when you've gotten into the bad region, you know it. You can see it immediately. It's just defined as the time you spend in the spike region, so then you just abort the algorithm.
If it's a black box, how do you even... You don't know if it's you don't know that it has a spike. I mean, that you're sort of treating that as a toy problem, of course. You could just output the answer, but you shouldn't how are you going to know that you're going to be in the bad region if you don't use the specific form of the Hamiltonian that you're?
Okay, that is also a good question. So, I mean, I think that similar to the number of steps we need in the adiabatic path, this is something that if you have a true black box, you're going to need to do multiple runs. You know, that's the only way to see it. So yeah, we do have to be careful qualifying the order n to the 7th, but I think it's a reasonably black box approach.
And my slightly less mean question was, so given that you have put all this effort into making it relatively black box, I mean, trying carefully not to exploit that. So can you then go back the other way, or have you thought about, say, okay, take your proof technique and then just see how far you can push how far does it generalize to other distributions where it will just go through again?
Yeah, I mean, I think that's very interesting, and in theory, the machinery could work. It doesn't depend on bit symmetry, but the question is, can we get these examples? So, for example, these weak cluster instances, I've thought a bit about that, but it's very hard to see how we can fully understand the quantum wave functions well enough to apply these techniques. So, what I would like to work towards is making these techniques a little less sensitive to needing to know all these details of the quantum system so that we can move to less exactly solvable systems.
But I guess you could also start with any exactly solvable system and just essentially you're sort of adding a perturbation to something exactly solvable and showing that things still go through.
Essentially.
So you could start with any exactly solvable and
Yeah, I mean, so we should be careful about calling it a perturbation because the spike term is tremendously large when you're sitting on it. But yes, one could think about this, and I think the other important question is, would these exactly solvable instances be sort of prototypical of interesting quantum annealing problems? If you know of any, then sure, talk about it, and we can maybe apply some of this.
Okay, thank you, Elizabeth.
Thank you.
Thank you so much.